In this part of the video lesson, we are going to talk about atomic mass. An atomic mass is the standard in which we represent the masses of elements and their corresponding atoms. So first of all, atomic mass. Sometimes we'll also refer to this as the relative atomic mass. It is a scale, and the units for the scale is just simply AMUs. And the way the scale was created, it was a standard based upon the carbon-12 atom. The carbon-12 isotope has 6 protons, 6 neutrons, and 6 electrons in it. So in defining this standard, they said a carbon-12 atom is equal to exactly 12 AMUs. Therefore, 1 AMU is equal to 1/12 of a carbon atom. Now, what does all that mean? Well, remember back in section 2, we looked at how to calculate the mass of one individual proton or the mass of one individual electron, and that was kind of difficult. Those are really, really super small numbers that we've looked at the end of section 2, and so it's kind of tough to deal with. If we were to say, it's a lot easier to say a carbon atom has a mass of 12 AMUs than to say it has a mass of 1.992 times 10 to the minus 29 grams. So it's a simpler scale. It's an easy way to represent numbers. Now, what we have right here, 1 AMU is equal to 1.660 times 10 to the minus 27 kilograms, or 1.660 times 10 to the minus 24 grams. That is a conversion factor, and that could be useful as we start to do other calculations. Now, what we're doing here is we're just kind of talking about how we use this scale, how it's presented on the periodic table, and then it's kind of the backdoor stuff. Once we kind of understand this, then we'll sort of move on to other things. So let's make a comparison here. Let's say we actually looked at a carbon isotope, or actually 2 of those isotopes. So remember, we said about isotopes, they are elements that have a different number of neutrons, therefore their masses are not equal. So what we're going to do here is you need to look up the individual mass for a proton, an individual mass for a neutron, an individual mass for electron. So what you're going to do is back on page 76, okay, I want you to look those numbers up, and I want you to actually multiply out a carbon-12 atom that has 6 protons, 6 neutrons, and 6 electrons, and see what your answer is in terms of AMUs, see what your answer is in terms of kilograms, and see what your answer is in terms of grams. Then I want you to do the same thing for a carbon-13 atom, except now we see 7 neutrons. Now, the point of this, and again, you don't have to go back and do all these, but the point of this is we've got 2 isotopes. Well, then we're going to get an average. Okay? Well, we're not going to put on a periodic table every single carbon isotope's numbers. We're not going to put on the periodic table every single oxygen isotope's numbers. What's on the periodic table is actually an average of all the isotopes. Because again, otherwise our periodic table would be pretty huge. So we'd have all these numbers that would be listed. So that's what we're going to focus on here, is what's the number on the periodic table? Well, it's an average. Now, here's what we want to do is when we talk about this average, what kind of an average? It's not a simple average. It's actually a weighted average. Now, what's a good comparison? Your GPA. An A in an honors class is worth more than an A in a regular class. A B in an AP class is worth more than a B in an honors class. So when we start to figure out, well, what is the average of all the types of carbon, we have to take into account, well, how much carbon is there of each type? To give you a comparison to that, okay, what we'll do is we'll look at, the book uses a simple example of marbles. Again, we could use GPA for that. Obviously you guys, I can't calculate GPAs because there's so many different scales now between AP and honors and all that stuff. But anyways, let's say we're doing marbles. So here's the example in the book. Let's say you had 75 marbles that had average that were 3 grams each, and you had 25 marbles that were 2 grams each. What would be the average mass of all those marbles? So some of you probably right now could pick up your calculator, figure out that number, okay, and get an average. And I'll have you do that here in a second. Let's say you had another situation. You had 67 marbles that were 3 grams and 39 marbles that were 2 grams. Our average is not going to be 2.5. And I think we'd agree it's not going to be 2.5 in either situation. So here's what I want you to do. I'm going to pause this, and I want you to actually solve for the average in both cases and sort of think about how you did that step. Okay, so we look here, what your calculation would have been is something very similar to this. You just said, okay, 75 times 3.0 grams plus 25 times 2.0 grams. That equals whatever our total is. We're going to divide by 100, and we get an average of 2.8 grams. Get rounded significant figures because of the 2 digits. Say you get, then for the other one, you would have done 67 times 3.0 plus 39 times 2.0. That equaled 279. You're going to divide by 106 because that's how many of our objects there were. And our average now is 2.6 grams. And so we can see here in the first example, it's a slightly closer to 3.0 because there's more of the 3.0 marbles. In the second example, the average is a little bit closer to 2.5 because we're not quite 50-50, 60-40 almost. So we're going to see that slightly weighted higher than halfway in between. Okay? So again, simple math calculation. Well, in chemistry, we're not going to count atoms. What we're going to do is we're going to look at percentages. So let's say we have 2 isotopes. We have, we're going to measure their abundance. So let's just give one other comparison. Let's say we have marbles, and we have 46% of the marbles are 4 grams, and 54% of the marbles are 2.5 grams. What's the average now? Again, it's not 4.0 plus 2.5 divided by 2 because there are not equal amounts. What are we going to do here? We're going to take 4.0 times the decimal equivalent plus 2.5 times the decimal equivalent. Now, when we get this answer, we need to think about what does this number tell us. So if we take 4.0 times the decimal equivalent plus 2.5 times the decimal equivalent, we get 3.19 for an answer. Now, rounding significant figures, 3.19 becomes 3.2. So our average for this mixture is 3.2 grams. That is what we're trying to do here when we talk about atoms, is we are not going to be able to count individual atoms, so we're going to look at percentages. Number 2, because the isotopes are not equal, we're going to have different amounts of each isotope. And if we have different amounts of each isotope, we're going to have a weighted average, not a simple average. So what does that really lead to? That relates to this equation here. The weighted average for our purposes is equal to the abundance or the amount of the first object times its mass, again, since we're sort of measuring masses, plus the abundance of the second object times its mass, plus the third, and so on and so forth. Now, if we're talking about in isotopes in chemistry, we're talking about amounts or abundances. We're talking about percentages. So the thing we want to do is we want to deal with the decimal equivalent of a percentage, not the actual percentage, okay, not 50%, not 40%, but the decimal equivalent of that. So what you can do, and this is something we will talk about in class, on page 82, they have a chart of several different isotopes, their atomic mass, and their average atomic mass. And you can see through those calculations here a little bit about how we get those true averages, because that number, the average atomic mass, is what gets put on the periodic table. So hopefully that's gives you a little bit of background information on how we are going to report numbers on the periodic table, how it's difficult to put a lot of numbers on there. So we're going to try and be very specific with the numbers that are placed on there so that we have a clear understanding of what we're using.